Okay, so hopefully today I did all these steps to record the class properly. So I believe next Monday is a midterm, right? February 8. So February 9, okay. So I posted a study guide. Midterm is going to be in-class exam, 2-hour exam. So it's physical exam. I give you physical copy of the exam and you write it in physical paper and give it back to me. So everything that I cover up to today, before Monday, is in scope for the exam. And so if you study all the lectures, if you can grasp all the formulations and the derivations that I've done in the lectures, kind of study the material and kind of try out some of the sample problems from the study guide, then you should be in good shape. Like it's nothing is meant to be trick questions. It's mostly like checking your knowledge in kind of what I've kind of taught you, that you grasp the material. That's kind of the goal of the midterm. So make sure you kind of study all the material from the class lectures and the assignments. So the assignments in scope are the first assignment and the first lecture, and the homeworks that you've done also. Okay. Any questions about midterm? Like anything you want to know?
You said there was a study guide. Where is it?
It's in the announcements. So check the announcements. Yeah.
So I'm guessing it aims to cover like everything on the study guide.
In the study guide, so that's a good question. In the study guide, if you find a question that I haven't covered in the syllabus so far, then you can ignore that. So I believe I put in a few questions on back propagation which I haven't covered yet, so that you don't have to study. Those are kind of meant to be sample questions. So in the study, so you should look at the study guide intersection of the what I've covered. So any question in the study guide that you see is I haven't covered yet, if you're unsure, ask me. But otherwise, if it's not covered yet, then we will have to work on the problems.
Additional question: would you be willing to tell us how many questions are on the test?
Yeah, I think it's going to be 100 points and like 10 questions, 10 points each. That's going to figure out. Yeah.
Are there any like practice questions, or is it just
the study guide for every section should have few practice questions. At the end of every section, I had some sample questions.
Will it be multiple choice, written?
Not really multiple choice questions, mostly written, and kind of expect to do some calculations, kind of simple derivations, like type of derivations that are done in class.
And so a calculator?
I don't think you would need a calculator, like nothing like no complex calculations, but you're free to bring one.
By the practice questions on the study guide, you mean you said there's multiple, but it looks like there's one per
Section?
Yes, and then 7 midterm style questions.
It's like a artist.
Yeah.
Okay.
Yeah, that would be the effect.
Those are the questions that you can practice. Yeah. Okay. So let's get started for today's class.
Did we figure out who's taking notes today, or?
Today he's all right. He's on the second one. So if anyone hasn't done his live note yet, it's you're up. Like next class, I'll pick whoever hasn't done it yet, and they must do it. Okay, so let's start. And if you have any more questions about the midterm, just message me on Discord. Yeah. Any more questions about the midterm? All right. So last class we started looking at the Hebbian learning algorithm. Okay, and today's plan is to wrap up Hebbian learning, and then we're going to start talking about universal approximation of a neural network. Kind of there'll be three sections here. One, universality using relu activation, sigmoid activation, and part C we'll talk about universality of boolean logic. Okay, so that's what I want to cover today, and this might spill into next class after the midterm. So, kind of radial basis function. So universal approximation theorem, I'm going to call it UAT. RBF as an example of UAT. Okay, and these will be clear as we go. Yeah.
Two things. One, what did you say about the midterm exam?
Sorry.
Did you say some portion of this was not on the midterm? Or?
Oh,
I don't know
if
if I
anything that I like the part B, if I cannot cover today, then it won't be in the midterm.
Okay. And then also, did you start the Zoom recording for?
Yeah, I think so. Good call. Let's double check.
Blinking time seems to okay, so.
Yeah, I think we're good. Okay, so Hebbian learning. So as a recap, last class we talked about the Hebbian learning rule, and the phrase associated with Hebbian learning is neurons that fire together, wire together. So if two neurons are activated at the same time, then the weight gets strengthened, right? So we increase the weight in proportion to the two neurons. And now if I have kind of a network where I have some input, right? Some input, let's say in dimension like an r-dimensional input, right? And then I want to map it to some output, and that can be in dimension, let's say RS, right? Let's use something. Let's use a vector P and a vector N as the output, just so that I'm consistent with the notation in the book. So I shared a link to a book chapter. So for Hebbian learning, that's required reading for you. And you also need it for the assignment. So make sure you read that chapter. So, and then my mapping is kind of a weight matrix W, and then we require, due to matrix algebra, we require this to belong to the space of. So my output N is a matrix multiplied by the input vector P, right? And then what do I need this? What should be the dimension of W for this to make sense? So W multiplies P, right? So P is in dimension R, right? So this is R by 1, and that means the second dimension of W needs to be R, and the first dimension needs to be S. So it's S by R, okay? Okay. So that's my model, okay? And here I'm not considering any non-linearities. It's just a linear map. And in the learning problem, I would have some pair of inputs and outputs. Okay. So P is the input and P is an output label or an output vector. P2, P2, up to, and let's say I have Q pairs. Right? And then we talked about the learning rule, right? So the learning rule is we initialize W to be 0, right? And then for an input output pair, Pi, Ti, right? So when I look at my input, you consider this as a kind of a collection of input neurons, and this you can think of a collection of output neurons. So you expect that in the network, when you see this pattern, you expect this to fire up. So you want these to be fired together, or the weight between this and this, right, should be decided by the strength of these two or the multiplication of these two, right? So we increase in the weight is proportional to Ti transpose Pi, right? And this, everyone remember why we have this particular form, T transpose P? Because that's the only way to match the dimension of W with this object. So this cannot be a scalar. We cannot do a dot product because we are adding this to a matrix. So it has to have the same dimension of the matrix. So T has dimension S by 1, right? So is this correct, or I think I did it wrong, right? Yep. So this would be an inner product, right? Yeah, this will create a scalar. So I need to fix that. So W is R by S. So I can decompose it into R by 1 and 1 by S, right? So R is the input dimension. So R by 1, this matches the dimension of P. So this is incorrect, and this should be Pi, and this matches the dimension of T transpose. So Pi transpose, and this will be a matrix, right? This is also known as an outer product because it's an outer product of the matrix. Okay. And now for all the Q input output pairs, I'm just going to keep adding them until I get the final weight value, right? So that means my final weight after learning, the learning algorithm is I go through every input output pair and update the weight, just like in perceptron. In perceptron there is an error feedback. We only update if there is a feedback. But here we update, we always update. For every input output pair, we update based on this rule. So the final weight is going to be for every input-output pair I have, I'm just going to compute this outer product and add it to my weights. Okay? And now that's my learned weights. Okay? This is, and in this case, I run this algorithm for every input-output pair, compute the outer product and add it to the matrix, and at the end of this round, I've learned my weights for my algorithm, right? And now if I have a new pair, you have a new input, right? Let's say it's some pj, right? Then I want to predict my corresponding output, tj. So then I would just apply this weight there, right? So I would say my prediction the predicted value is basically w times pj. And my expectation is this should be similar to my actual target output, tj. Right? That's the learning process. Yeah.
Can you explain why it's pi-ti transpose? I thought it was ti transpose pi, because the weights is s by r, right?
Let's see. You might be correct. So let's check it carefully. What are my dimensions? So P is in, P belongs to R dimension, right? Let me check my notes just to make sure I'm correct. And then T belongs to R to the power S. W is in R to the power S by R. So S by R we decompose at S by 1 and 1 by R. So this is T bar and this is P transpose. So my weight change should be T bar. That's correct, I think. So let's see. Right. So you're right. Thank you. That's good. That means you're paying attention in class. So it should be, what is it?
Ti, pi.
Ti, pi. Very good. So the W is summation Q pi transpose. Okay, very good. So this is our weight vector, and now let's kind of check how well does this do. So the first thing we want to check is for the given inputs that I have, right? I have a given set of Q input-output pairs. If I apply one of these inputs, I should get the corresponding output, right? So if I apply W to my first pair, I'm expecting to get my first target output vector. Okay, and now for this algorithm, the condition is that this will be true. You will get an exact WPI is going to be exactly TI for I belonging to all the input pairs, if and only if the PIs, the input vectors, are orthonormal, which means that they need to be completely perpendicular to each other, or in other words, they should form a full basis of W. Okay. So can someone tell me what is going to be the rank of this matrix W? R? Right. It should be kind of the minimum of R and S. Yes. The rank would actually depend on so the rank of W has to be less than or equal to the minimum of R and S. And there is also another constraint on the rank, which is it has to be equal to Q, the number of input output pairs. Right? And the reason for that is the construction of these outer products. Each of these outer products is rank 1. Because if you look at this, if you calculate this outer product, you'll see that all the rows are linear combinations of each other. So there is just one linearly independent column or vector or row. So each of these are rank 1, and if you add Q rank 1 matrices, you get rank Q. So that's why the rank of W is Q. And then Q, that means Q would actually be less than or equal to minimum of R and S. Okay? And now we assume that Pi is orthonormal right? That means if I take a set of vectors Pi and Pj and I compute the inner product, then this is going to be the Dirac delta function, right? So if that's the case, now let's see what happens to if I apply any of the inputs from my input collection. Now if I want to apply this to this network, then I need to compute W times Pk. Okay, so this is my prediction. And I want to see whether it matches the output. If it matches the output, that means I've successfully learned the input of the pattern. Okay? So, and then this is I equal to 1 to Q. What is my form? So summation I equal to 1 to Q Pi transpose Pi transpose, and then there is a Pk out here, right? And then this Pk does not depend on I, so I can put it inside the summation. So if I put it inside the summation, then this is going to be 1 to Q Pi transpose Pk. Okay, and this is an inner product between two input vectors, and we say they're orthonormal, right? Which means that this is 0 if I is not equal to k, and if I is equal to k, then it's 1. So the only term that survives out of here is which term? One where I is equal to k. Right? That was the trick that I showed you last time. So this should be basically the only surviving term is tk. And you can see that this was actually the output that I provided. So with this construction, the network kind of memorizes all the input. Kind of, if you give it one of the sample inputs that you've given it, it correctly produces the correct output. But there is a condition. The condition is that the input all the input vectors need to be orthonormal. So if all the input vectors are kind of orthogonal to each other, then you can properly memorize all the patterns in this network. Otherwise, there will be errors. Okay, so if all pi are not orthogonal, then there will be some approximation error. Okay. So let's now try to understand this error. So what we have, this weight matrix, and we can apply a vector, and we expect to get the corresponding output, right? So let's take all our input vectors and kind of pile them up in a matrix. Okay. And then if I do this, then I can write it like this. So the first vector, the second vector, up to the qth vector, right? If I pile them up as a matrix and left multiply by w, then this should be equal to the corresponding output vectors, right? And let's call this a vector t. So that means I have w times p equal to this t matrix. Okay. And now we want to answer the question, when all the input vectors are not completely orthogonal, then what type of error do I get? Right? I expect that this weight, if we cannot make the approximation error completely zero, we want to minimize the error as much as possible, right? And we will see that this construction will actually do that. Okay. So let's say, so now let's kind of formulate this as a kind of a loss minimization problem, right? We have our inputs and outputs. We formulate a loss function, and we want to minimize the loss. Okay. And basically, we want to kind of estimate W such that the total loss is minimum. Okay. What is the loss here? How do I get the loss? So I have these input-output pairs. Right? And then I want to apply this weight matrix to each input, right? So I'm going to apply W to, let's say, an input, one of the input vectors PQ, right? And that will be my estimated output, right? So this is my estimated output, and my true output is actually what I provided as in my input here, right? And I expect that I want to, so we showed that if all my input vectors are orthogonal, then with the previous learned matrix W, I can make these exactly the same for the input pairs, which are orthonormal. But if they're not orthonormal, then we need to do something more general. Okay? And our goal is that we want the W to be such that this target vector TQ hat and the actual output vector TQ, they should be as close as possible. So if there are two vectors, I just want to take the difference of these two vectors, take the norm, and make that norm as small as possible. And that's how I define the loss. So my loss is going to be some function of this weight matrix W, and I'm going to compute this loss for all my input-output pairs. I have few of them, and for each of them, I compute the difference between my qth output target minus my estimated target, right? And these are vectors. I'm going to take the norm of the vector and just square them. Okay. And then what can I do here? I can actually do this as q minus, and then we know that we estimate this is a function of W, so I need to somehow bring the W here. So the W comes from the estimation PQ hat, which is W times the input vector PQ. Right? So I'm going to plug that in here. We take the norm of this. Okay. So this is my FW. Okay. And now I want to, so now I have this equation of the norm of these vector differences. I want to make this a bit more compact. I want to kind of compress them into a kind of a matrix equation. And we will see why we do that. It makes the math much easier. But earlier we defined a matrix T to be all the input vectors aligned with each other, right? Right? And now if I take this and let's say I subtract from here W times all the input vectors, right? Let's look at this expression, right? So this is like all the target output columns minus W times all the target input columns. So if I do the math, how do I do this math? The first column is going to be basically T1 minus WP1, right? As a vector. So as a vector, this is going to be T1 minus WP1. And then the second column is T2 minus WP2. And then the last column is TQ minus WPQ. Okay?
You're adding each one of those? They're in a matrix.
So basically I'm doing a matrix computation. So I have, this is my first column of this matrix, and this is the second column of the second matrix. And with the W inside, you can multiply W by 2 and get another column. So then it's going to take each column and not subtract from each other. So this is again, these are kind of a bunch of columns. Right? And now if you think about it, So I want to, so what I want to do here is this whole thing here. This is, you have multiple columns, so you have, and each of these, and you have a number of rows, right? So you have to matrix, right? And now I want to define a norm of this matrix. Okay. So if I have a matrix A, I can define what is called a Frobenius norm of A, right? And this is basically you vectorize matrix A and you take the norm, the vector norm of it. Okay. Example, let's say I have a vector 1, 2, 3, 4, a matrix 1, 2, 3, 4, right? And I can think of this as basically stacking all the columns on top of each other. So I do 1, 2, 4, and then it becomes a vector, right? And now if I want to take the norm of this vector, what would I do? I would just take all these numbers, square them, and add them up, and do the square, right? So this is only 1 square plus 2 square plus 3 square plus 2 square, and then I take the square root. Okay. So now if we go back to our expression, what we have is a P1 minus W P1, that's the first column, P2 minus W P2, and then I have P2 minus W P2. So if I vectorize this, right, what do I get? I basically get a stack of columns. So I have, so if I vectorize this, I get P1 minus W P1, that is the first vector, then I stack it on top of P2 minus W P2, that's the second vector, up to P2 minus W P2, that's my last vector. Right? And then now, if I take the norm of this whole thing, it's basically taking the norm of each column vector and finding out. So this will just be, I'm going to show you how you can do 1 to 2, 5, plus W, 5, vector norm square. Okay? So that means finally what I get is my matrices P minus WP, the norm of that is basically, this is exactly what I decided to be the loss function, f of W. The solution f of 1 to 0, we have this f of 5. Alright. So that's my final information. Now, if I want this error to be 0, right? If I want this error to be 0, then what do I need? I need P minus WP to be 0, right? Or P equal to WP, right? And then from here I want to find out what is W. Okay. How can I extract W from this equation? P equal to WP. What do I do here? W equal to P, and from here I will define W. These are the matrices. Inverse. Now, again, this is where we need our some of previous constructions. So I need to what I need to do is W needs to be, I need this to be the inverse. Okay? So what do we need to check about P? Can we take an inverse? X square. The matrix P has to be square, but what is the dimension of P? Because that P was kind of stacking the inputs together. Right? So the P matrix was I was stacking all the inputs. So P is the dimension of the input is R. So it's R times P. That means that in general, the P matrix is not square. The case where it actually works out is, let's say, we talked about this, right? When we did the previous construction, we said that W is R by S, right? And then Q is the rank. Rank is Q. And then if that was equal to mu of R comma S, right? In that case, we could have that mu equal to R, and then we will be able to actually invert it, right? Yeah. Mu of R and S. And that's the case where my vectors are orthogonal. Yeah. So yeah. And that's the case where actually I can find an inverse and everything works out. But if in general, the R and Q dimensions won't match. So it will be a rectangular matrix. So what now we know what happens what to do with the rectangular matrix. When you get an inverse rectangular matrix, what we want to use the same inverse. So we have that's the main application of the single inverse. So instead of P inverse, we use the single inverse P gap. That means so it is going to W equal to P. That means the P inverse is going to be the more than the inverse of the single inverse. Okay? And this is going to be the solution that in this case the P, all the P inputs, they can still be, they can be arbitrarily taken off the whole. But even if they are not optimal, this will actually minimize the consequences of it. Right? It's kind of similar to a kind of a square, least squares problem. And then, if you remember, the equation for this was you get the transpose of P multiplied to P, and then you have an inverse, and then you need P transpose, right? And that means from here, your final equation will be W equal to P transpose P inverse P transpose again. So find out W will be P times P transpose P inverse P transpose. Okay. And that will be your most inverse solution. Yeah. This is your lower case. Right? Basically, it's all I find it's not a very simple. Yeah, good question. So the single inverse of the matrix A is this denoted by A, and now that B is kind of a cross with the algebra value is normal income. It's kind of like a glass line. This line is going to come out closer to the top. Yeah. So you're assuming that is you still got the same question. When you compute the adjoint, or when you compute the C inverse, the technical definition from P transpose P you only have to know that the alpha small alpha is high to make sure that all the angles are not. So that's the most general definition of the C inverse. Like here I'm adding that P transpose P gets like a small matrix when you can invert it. Yeah. But technically you are executing correct strength. Yeah. Exactly. So your true it will be something like limit x comes to 0 P transpose P plus some epsilon times the identity matrix. Your inverse P transpose. That's your exact equation. And then what you do is then like you actually compute this inverse. Then do some arbitrary small epsilon. Compute this matrix. Check whether it's non-zero one. If it's 0, then you cannot increase a bit. And until it becomes, until it becomes non-zero. Yeah. Yeah. Good question. So you will also find this in the book chapter that I shared that has just read the book chapter. It has some more numerical examples. The last class I also showed you how you can learn the AND gate with this algorithm. So practice like some other gates like or not gates. Okay. So I've told you everything about Hebbian learning. I will start on the talking about this is a good time for a break maybe. That we have then we start again at 9 p.m. So let's take a break now and come back at 9 p.m. This is a form of compute. from the area, and the other one is like is vectorized. Creating is like a number or something, something like that. I did that, like so you have to have the both. Because I saw that before. Oh, I see. So I lost points. Okay. So you want to didn't have it. Oh, I see. So it's in the points. Yeah, it's fine. I did one from okay, so you just comment it out because you want to implement anything into the one. Send me an email or a message, and that's where you can have the points. It's going to be how many points you missed for that, and I'll do that. You know what it is. So you said that you missed something. Yeah. Problems in the book that you don't have that book have some problems, so I followed the video line stuff I followed like very close to the book, especially when I lecture that chapter. For the other topics, you also find work-out examples in the book, so I would recommend taking a look at my notes. All the notes that we do, all the calculations, all the sliders, there should be still like this. But the later that has some problems that goes through the types of problems on a particular get. So trying to think of some variation of problems is what happens. Yeah, to understand all the properties that are done. The variations. I won't give you like a huge variation. I'm just gonna maybe follow what I taught you in class. So small things from the class. You might get nothing complex. Some modifications in the class. We covered a bit of linear algebra. So make sure you brush up on the all this stuff. For the conceptual, we quite a bit of detail and Hebbian learning to make sure that you understand the concept of convergence, especially with the whole exam is next Monday, right? If you want to start putting each other, there's some more time for you homework. If you want to start. Yeah, but I would like to put it in this I'm not exactly following the book. So I'll send you a link on something on dividing the Hebbian that you use the vector other vector is before and outside. That's the vector of the Should we start? So let's restart the second part of today's lecture. Let's check whether sharing is there. Still recording. Okay. So finally, after this many classes, we're going to move from a single neuron object to a collection of neurons. Like stacking and doing with more power. Right? So far what have we done? We've done kind of the perceptron, we've developed it, and then we make a Hebbian neuron. The real power awareness comes when you actually compose it together. Right? So when you look at the perceptron, right? What is the perceptron? You can think of it as a unit where you have inputs with weights. And then you pass it to a threshold function, right? It's like a step function, right? If the mu transpose x is greater than 0, you say it's positive. If it's less than 0, you say it's negative, right? So what you're kind of doing is you kind of, and there are many names for this, like a hard limit or like a threshold function. There are many names for this purpose. So basically, in terms of what we're doing is that you can say it's like a indicator function. So the output is like an indicator of this buffer, right? It becomes 1 if you can also say it becomes 1 if it's equal to 0 and 0 otherwise. Right? That's another way of saying that. So if I plot my dimensions here, and look here, then when the dot product is less than 0, like this is your y hat. If it's less than 0, then it's you can call it 0, but then if it becomes positive, then suddenly you have this jump. Right? You jump. Not one is negative, your output is 0. So here again I'm going from plus minus 1 to 0 and 1. Like we already getting about perceptron, so now I can change the value and now the same class. Right? So when it's on this is my negative side, so it's negative means that your function is 0, but suddenly when you have a sharp jump here, then you jump to 1. Okay? Get a question here. So what do you mean there is one difference in step function? What is the other step function? No, that means choosing the period of square. Yeah, the two extremes you can define like this could be the zeros and the other one minus 1. This one, right? You can decide where you kind of only point to this equation. Right. There are some calculations, but until you can go into the so you have 2 levels and you can jump over those levels. It's a sharp jump. This one. So overall, this is like a single neuron to me, right? And now we want to understand what happens when we kind of like combine these together, right? One thing that we did, so we're going to talk about 3 things. One is universal boolean logic. Okay, that's the first thing that we want to discuss. Because if you think about this neuron computation, right? If you study electrical circuits or logic design, you know that there are some basic logics, right? You have to block not gate, AND gate, OR gate. If you can build these gates, then any other complicated Boolean logic you can implement using these building blocks. Right? Now, when we talk about perceptron, we showed that the perceptron is a single neuron, right? The perceptron cannot learn itself. Right? We showed that with an example, right? Just because there is no linear classifier, that's the correct stuff, positive linear examples. Right? But that's a limitation only if we restrict ourselves to a single neuron. Right? We also know that the perceptron can learn AND gates or gates and NOT gates. Right? In the homework we explicitly constructed the one parameter that we realize the AND gate out, right? And we put it in process. So that means I can build this is possible, I can build a neuron that implements the OR, right? I can give it 2 inputs, right? And an output I should get the OR of x1 and x2, right? I can build that. Similarly, I can build an AND gate as a neuron. So I can build an AND perceptron and an OR perceptron, right? And now, if I think about the external function, which I did not do with a single neuron, right? Now only if I plot, if I kind of look at truth table for this call this function of x1 and x2, right? So I can express this function of XOR, right? What do I do? This becomes 1 for only these rows, right? So I can enumerate these rows. How can I write this row in terms of x1 and x2? So I want to find out if we want when this is satisfied and this is satisfied. And all of two terms. What is the first term going to be for this row? X2 and not x1. Right? X1 bar x2. Right? Because now if I check, if I have the first row which was 0, then this will be 1, it is 0, so 0. So that will not be correct. And then if I check this one, second row, then x1 is 0, so x1 is 1, and x2 is 1, so it will be 1. So I get like 1 is expected. So that's for this term, I need something for this term. So what would I have for this term? Vice versa. Vice versa, yeah. So it's going to be x1, x2 bar. And then if I can check what happens with the last one, if both x1 and x2 are 1, then here x1 is 1, so it's 0, so this term is 0. And here x2 is 1, so x2 bar is 0, so this is 0. So 0 plus 0 is 0. So this term exactly equals the x1 logic. And now, how do I construct f? I can now take x1 and pass it through a not p1, right? And I will get x1 bar. And then that I can pass through a and gate, right? Just to make it more like easier, I can say I'm going to expand my input, right? I'm going to expand it to include my expanding input set. And now what I'm going to do is I'm going to build a network over there, right? So I'm going to take x1 bar and x2 and pass them to an AND gate, right? And then I take x1 and x2 bar, pass them to another AND gate, and these are go to an OR gate, and that's my answer for XOR of. So that I actually now doing I compose the single neurons together to form a bigger neural network, and then this actually will have a free tensor function. So this means that any Boolean function, as long as you can express them in terms of like OR of AND terms, right? A bunch of AND terms, and that's a universal fact that you can get any Boolean function. And then this is in this form where you have a bunch of nodes that are added together and then plus all of them. And the terms can have either a ground, either a variable or a station. But if you do that, you can actually draw out this graph, and then you get the neural network against that function. So this tells us that all possible Boolean expressions, how much complicated it can be, you can always realize that in the neural network. The neural network can do all sorts of Boolean computation. Okay. So now we know that even though when this case paper show that receiving perception cannot solve XOR network that causes a chapter of all combinatorial research, right? It's not as bad as you think, because you can actually just, in this case, just get 3 neurons properly wired together and then you can solve the XOR problem. class. Right? It's a binary classification problem. And if the inputs are separate only between classes, I can find the system one here and solve the classification problem. Right? And now you know that if I take a single perceptron, right, that gives me linear boundary, but if I have a more complex problem, I can somehow decompose it into smaller perceptron type problems. Right? So if I tell you that you need to solve this problem where you have a bunch of inputs here, and this is surrounded by an outer circle of cross classes, right? Now we can look here as we can easily argue that we cannot find the libraries of these classes, right? But we can use neurons to solve this problem. Can anyone suggest a strategy for solving this problem? I want to separate the circle class from the cross class. Yeah, somehow a kind of single class. Yeah, exactly. So basically, we can do something like this. Like, technically, I would like to do a circle, but a circle means you need an infinite number of neurons. You don't need to do that, right? So what you can do basically do something like this, right? So kind of think of this as one line, and another line, another line, another line, another line one. All right? And now, I don't know linear. So what I would do is that I can name these, right? This can be like H, and call this like line 1, H2, H3, H4, H5, right? And let's say like, and let's just force it to that the inside is kind of a positive side of each of these lines. I can make that assumption, right? And that means that I basically now have 1, 2, 3, 4, 5 perceptrons. And if all the perceptrons come out to be positive, then I was having the linear inside class with a circle class. But at least one of them is negative, then I would be in downside class. Right? So for example, if I have a point out here, right, then corresponding to this H2 for that particular point out there, H2 become negative, and then I would say I'm in the cross class, right? So I get to draw a cross here, right? And then let's say I have a new point here, and I want to find out what class it belongs to. Right? For this new point, I will have learned the ways for all of these perceptrons, right? And for each of them, I can copy the buffer with that body. And if all of them are pointing inside a positive, then I will say that I belong to this imaginary class. Okay? So my network would go something like this. Right? So I have some input. Some input, like some numerical space, right? And this input goes through how many neurons? I can pass it with 5 neurons, right? So like let's call them with H1, H2, up to H5. So this input happens to all of them, right? And then now I need to do some sort of, I can do just like a simple AND here, right? I can pass them through like think of extending AND to multiple inputs, like you can build that, where the AND is passed to all the inputs of 1, and is zero when at least one is not one. Right? You can easily use that one. Right? And you can easily extend that, right? So I can then at this layer, or if you want, you can do it few at a time, right? So you can classify right? Which connects all of them, right? And this and one means that so let's say this is the weight vector 1, this is the weight vector 2, and this is the weight vector 5. So this is one if W1 transpose X is equal to 0 and W2 transpose X is equal to 0 up to W5 transpose X is equal to 0. So all of them are divisible 0. That means I will say around that that's only one to the approximation. Right? But if I at least, but if it's a point outside of this decagon, like here, if I have a point here, then there is at least one line which will be negative, right? And I can find that I can say that this line, this hyperplane, this hyperplane, this side is positive, and this negative, so this will become 0. So that particular, like this is h5, so that cross h5 is going to be 0, and the others will here, but when you add the 0, then you can get a 0. So you can use the 0 plus. You only get the inside when all of these zeros file, which is fantastic for the regular side is possible for all the sides. So this is kind of, you can learn any complex distribution boundary. So when you get the classification where you are not using a boundary, you can kind of compose a lot of zeros and you solve the problem. Okay. So when you have a classification, you can actually solve within your network. And now, the question you can ask is, we can solve any classification problem this way. How it is, right? Is there even a human as a part to solve the problem, or can we do that would be the computation? Okay? And like just for fun, like if you believe this so far that we can learn this pentagonal non-linear structure, right? And then like there is no stopping us, right? We could even think about a structure like this, right? That kind of think of like that, kind of a linear structure. Yeah. And one is variable, but there is some idea, maybe I should be able to design the vectors and tell me the interior of this linear scalable complex pixelator. So if I have an image of a pattern or any structure, I can say what pixels are inside the image and what my thoughts like that. I should understand a lot of concepts for that. So we talked about the power of real networks for solving boolean logic or classification problems. Right? We argued that you can compose a bunch of perceptrons to solve any type of like a decision problem, or you decide whether at some point I am doing all the way around the way around. So even if you have a non-linear definition boundary, you can kind of approximate that as what's it called? Like I hear about your pentagon, but think about like polygon. Like any nonlinear boundary I can approximate with a polynomial boundary. And from that, I can each have the polygon of given one. And if I outcome there, I can get the buffer distribution. Right? So that's all over. And the next question is, can a neural network learn a continuous function? Right? So this is where, so we talked about the power networks for the classification problems. Classification problem is when you need to be somehow divided by the size of the house or the number of people. Right? But it always use a neural network to approximate some sort of continuous function. Right? So my continuous function will look something like this. Like this is like f, let's say we use x. So let's say this is my target function, and I want to learn that function where I only have a finite number of sample inputs and outputs, right? So can my input, for example, might look something like this, where I'm going to have some points here, right? Something like that, right? Now, if I didn't know, so this is my actual function, and we are sampling. And from the samples, I have some noise, right? So like then I get these multiple inputs that I have, and from this I'm supposed to figure out this function. Right? The question is, can you know that what always do that? If I didn't know anything to verify this data, my mind will be like a linear function. But you can see that with the linear function, I can calculate loss on this dimensions. Right? So obviously we need some sort of non-linearity. Right? So we need to answer the question, can we kind of deal with the nonlinearity of the neurons, kind of stack and program it somehow, but kind of arbitrarily approximate subject with the nonlinearity. Okay? So we come to the approximation. Approximating a continuous function, and then I want to kind of talk about index approximations. So it also is clear that if you want to kind of approximate such a nonlinear function, you cannot just have linear units. Right? If you take your input and just pass it through a kind of a linear transformation, you cannot really represent the nonlinearity in a curve. Right? That's not impossible. So if you have a nonlinear pattern, like you need some sort of nonlinearity. Okay, so the two types of nonlinearities that we have that are very well known is like relu activation, right, and a sigmoid. These are the ones that I'm going to talk about. Okay, so first let's talk about relu. Okay, relu stands for rectified linear unit. Okay, and we want to see if I have access to a kind of a relu nonlinearity, right? Can I approximate any function with a bunch of relu activations? So what does the function look like? So the relu of x is basically very simple. It's x if x is greater than or equal to 0. And it's 0 otherwise, right? So it clips all the negative values and only keeps the positive values. So the graph looks like this, right? This is x, this is value of x, right? And then I can talk about a relu neuron. A relu neuron. So previously we were talking about a perceptron as a neuron, right? How do we differentiate different neurons? we differentiate by the different non-linearities that we add at the end, right? So in perceptron, we have this hard threshold limit, right? Where positive values of the input give me one value, and the negative values give me another value, and there is discontinuity in between. But here, the relu neuron looks like this, right? We just have, similar to previously, we have like these inputs here that pass through a network, right? W1 up to WD. And then basically I then pass it through this relu activation. So it's kind of passing through a relu network, which means that the output is kind of relu of W transpose of X. Okay? So I first, just like a regular perceptron, when I get my input, I multiply it with my weight vector and I get this dot product. And the difference is what I do with the dot product. I can pass it through a hard threshold and get a perceptron, or I can pass it through a relu activation and get a different type of output. Right? So a relu neuron is basically this unit where I do the dot product with my weight vector and pass it through this relu function. And the relu function is defined up there. Right? So that means that my output of this neuron is going to be, it's going to be W transpose X if this is positive, and it's 0 otherwise. Okay? Does that make sense? So I'm changing from a hard threshold to this, like, a different type of non-linearity.
Do you have an example where like you want to choose this one versus
The kind of the one-line example is like, whenever you're building a neural network, always choose relu. That's the rule. Now there are lots of, I can give different types of intuition for that, and I'll give you one intuition now in terms of like the expressiveness of this. But like in actual reality, when you're building like large neural networks, the power of relu, there is some theoretical justification for that, and some of the theory gets really messy. But empirically, it has been shown that like anywhere you apply nonlinearity, the relu works very well. So there is a lot of empirical evidence that this is kind of the best nonlinearity to have in modern neural networks. It does have something to do with what is known as vanishing and exploding gradients. Right? We'll come to that, but when you have a very deep network, if you want to learn it, you need gradient information. You kind of do the forward pass, and at the end you get a loss, and from that loss you need to compute gradients and to propagate them backwards. The relu makes sure that you can actually propagate some signal, and you can learn something.
I ran into that problem in my project data set.
Yeah. So if you do like something like sigmoid, then whenever you have extreme values in a sigmoid, and I'll show that, your gradients become almost zero. So if the gradients are zero, there is no learning. You need like good gradient values to learn, and the relu kind of helps with that. But whenever in doubt, use relu. That's the thing that you take away from this course. Okay. So now so that's a good question, and now I want to kind of give you some intuition. Like this is not going to be a very rigorous argument. Like it's not easy to make rigorous arguments with relu just because it's such a complicated object mathematically. But like I want to show, kind of just give an idea of approximation with relu. So now our problem is that I have an arbitrary, like an extremely jagged nonlinear function. I want to kind of stack up a bunch of neurons so that I can actually learn that function or approximate the function properly. Right? So let's say for simplicity, I have just a single input. So I have input which is just a single number, and I'm trying to learn some function of x, right? Some unknown function of x, right? So if I have a single input, right? From that input, let's say I build one nonlinear function which is like a relu of some weight vector times the input, right? And in this case, you can think of this is basically just a single input, so it's just a single number. So I don't even need a transpose here. So W is just a real number, right? So W1 is a real number. So my problem is simplified. I'm just thinking about a single dimensional input. So W is just a single number that I need to choose, right? And if I think about this, let's say this is my X, right? This is my X, and I'm basically multiplying X by a parameter W, and then passing it through a relu, non-linearity. So it would look something like this. Like depending on W1, that input will look something like this. It could look something like my phi1 could be something like this. Like it's based on W1. There will be a point on this number line where W1 times X will be 0, right? And then I would have some point here. So this is where W1X is 0, and then I could get something like this, right? So here in this part, W1X is less than 0, and in this part, W1X is greater than 0, okay? And this point here, this point, and this slope, that depends on my parameter W1. So I can change W1 to change how much steep this is, or how much like flat this is. So I can change this dimension here. I can also choose where I place this threshold, right? And now what can I do? That's one, but from here I can, so this is my phi1 behavior, okay? And here I can do the same thing with a different relu. Let's call it W2X, right? And I can choose W2 such that that threshold is somewhere else, and this slope is also different, right? And depending on the sign of W, I can also get a function like this. So it could be something like this. Right? Where that means that in this region, W2X is greater than 0, and in this region, W2X is less than 0. That means that W1 and W2 probably have different signs, and I am allowed to choose that because I'm learning this network. And then I can have another one, phi3, which is going to be relu of WX, and I can make that something else, right? I can choose something like this, and then it could be something like that, right? So now what I can do is I can think about approximate my function of X as I build these values which have these kind of like single non-linearities at different points, and I can kind of weight them together and kind of combine them to kind of find a kind of a complex structure, right? So if from here, I can think about that I have these three different non-linearities, but I can try to add it up somehow. So this could be something like, so in this region I have this part, right? And then for some portion there is like everything is 0, and then at this point, this phi 3 kicks in, right? And then somewhere on this point, I have both phi 3 and phi 1, so I kind of get like a larger signal here, right? And then depending on another function, I might be able to do this or here, right? So I hope I can convince you that I can basically, depending on my input function, right, I should be able to kind of build these piecewise linear units, add them together, and approximate a continuous signal with a bunch of these linear signals, these linear lines, right? So that's kind of the idea of approximating any function, continuous function with these piecewise linear functions, right? So basically what I'm trying to say is that I want to approximate it with something like this. Let's say I have 1 equal to k of these relu units, right? And then here I can say I'm going to use a let's call this wi, and then inside that I have a relu, and the relu parameter I'm just going to call ai, and then this means that I'm trying to approximate the function with k relu neurons, and these ai's and wi's are my parameters for my network, right? So then, in terms of an architecture, what this would look like is my input comes in x, right? X can be a d-dimensional vector, and this goes through like this has a weight w1, and I have phi 1 of a1x, right, which is kind of a relu of a1x. This is my first relu neuron. I get w2, and here I get phi 2 of a2 of x. This is my second relu neuron, and I keep doing that until I have the kth one. So this will be phi k of ak of x, right? And then I can just do a kind of an addition here, right? I can add these together, and then I get my estimated output, right? And then I expect y to be an approximation of f of x. Okay? So one way to think about this is, let's have this function x, right, which looks like kind of a curve like this, right? And I want to approximate it. Yeah.
Oh, sorry, I just wanted you to scroll back a little bit.
Oh, okay.
You're blowing through the grass faster than I can tell you.
Okay, sorry. Yeah.
Okay, you're fine. Okay, thank you.
So if I want to approximate this function with a bunch of relu neurons, I can decide on, so as if you think about this argument, if I want to do a really good approximation, I'm going to need a huge number of these neurons. The more neurons I add, the more I can like think about the jagged stuff and model everything with a very small linear part and kind of add them together.
So the more you add, the more it looks
Yeah.
like a curve.
Yeah, more curvature you can get by the more piecewise components or relus that you add, the more curvature you can model. If you have just like few, then you can just do a few things. So you can think that and whenever you are kind of trying to approximate, you have some approximation error in mind, right? So for example, I could specify it as like some sort of uncertainty around my curve. I can say that I am allowed to kind of be within plus minus epsilon of this curve. So that's, as long as my approximation lies in this region, I would say I'm doing a good job.
And that
Right.
approximation is specific to the problem.
Yeah, that's like how much tolerance you have in your problem. Like, if for this to be really thin, you're gonna need a lot of resources.
Yeah.
But if this is wider, you use less resources. And now once you have this, right, you can say, okay, I'm gonna first model it using this line, right? and I can build that with one relu, and then the next part could be like this here, and then I could do something like this here, right? So the reason here I can do with only 3 is because there isn't that much curvature here, right? If you had something like something really jagged, right? Then you would kind of need to have something like this. You have to, every time there is a bounce, you'll have to have a different curve, right? You'll have to do something like this to properly model things, right? So you need more relu units there. But if you have access to an infinite, possibly infinite number of relu neurons, you can kind of approximate to any arbitrary precision, right? So that's kind of the rough idea of how a bunch of relu neurons, you can stack them together. And one thing to note here is that when we are stacking them, in this case we have my input layer, which is X, right? So typically the input layer, you think of this itself as kind of an input neuron or a bunch of neurons if X is high dimensional, right? So kind of the way you would think about this is like X1, X2 up to XD. These themselves are these input neurons, and they pass through these nonlinear units. There's 5K of them, right? And they all connect to these neurons, right? And then you have the final output neuron, which is kind of the summation or weighted summation of these relu neurons, right? So this could be like W1, W2, WK, and your Y is basically summation of I equal to 1 to K, WI, YI of AIX, right? So the A's are in this part here, right? So this would be A transpose because X is d-dimensional, so A also would be d-dimensional. Okay. So now what you have here is kind of, this is your input layer, this is your output layer, and you have one hidden layer here. So just a one layer network of hidden units, and just with that one layer, if you kind of make the height of this layer almost very infinite, you can model any continuous function. So to express any continuous function, that's all you need, just one layer. You don't need lots of depth to approximate. The power of the depth comes because if you just have one layer and you want really high precision, the number of neurons in this layer will have to be exponential. But if you have multiple layers, you can get away with like smaller number of neurons per layer and then kind of vertically stack them together and solve a similar problem. So that's more tractable. That's why we kind of have more depth. And the depth kind of helps us keep the count of neurons in each layer tractable. Okay? But this is the first kind of our first composition where we are composing all our power in a single layer of neurons, and we're going to stack them to almost infinite height, and that's enough for us to do any type of like classification or function approximation, right? So that's the idea of a continuous function approximation with a neural network. So in this sense, a neural network is a universal approximator. And there is a mathematical theorem called the universal approximation theorem, which proves for different types of non-linearities, where you have an arbitrary continuous function, and you can always approximate with a sum of piecewise linear like functions that are combined linearly, right? So it could be a relu non-linearity or a different type of non-linearity. Okay. So I want to start talking about the universal approximation theorem. And what I demonstrated to you with the relu networks is at one instance of this result, where any continuous function can be realized with a single neural network with relu activation. Proving that mathematically is hard, but you can get more intuition with a different type of nonlinearity, which we haven't talked about yet, but which is very, very crucial in kind of foundations of neural networks, and that is the sigmoid neuron. Okay? So what is the sigmoid neuron? The sigmoid is another nonlinearity, right? Its definition of this nonlinearity is the sigma of x is 1 divided by 1 plus e to the power minus x. Okay? That's the sigmoid neuron. So how does it work? It's similar to any other type of neuron, right? If you have a bunch of inputs, you pass them through a layer like this, and here your computation, let's say it is when you do this computation, you compute the value which is W transpose X, right? This is typically called a pre-activation. And then the pre-activation passes through this sigma function, and that's your activation. Okay, that's your activation. So that means if I compute this, then it would look like something like this. W transpose X is going to be 1 divided by 1 plus e to the minus W transpose X. Okay, what does this look like? This looks like something like this. It kind of looks something like this. So this is 1, and this is 0, and this is like 0.5. So this is X, and this is sigma of X. So if you plot this, then this is what it looks like, right? If you plot this function, this is what it looks like. And you can see that if you think about this, then this looks like continuous analog of a hard threshold. How do you think about that? When your X value is really large, then the sigma function, what happens to sigma when X is large? What is our sigma function? The sigma of X is 1 divided by 1 plus e to the power minus X, right? If X is very large, then e to the power minus a large number is what? 0.
Sorry, you said that. Oh, yeah.
When X is large, e to the minus X tends to 0. So it's 1 divided by 1 plus 0, so sigma X converges to 1. So for large values, you convert to 1. And if X is really negative value, yeah?
Hold on, sorry. But this is essentially giving you the curve you're trying to replicate with relu.
This is a different type of nonlinearity. We are in a different ground. We're going to build neural networks with sigmoid only now.
Okay.
So when X is negative, then what happens here? Then a negative and minus X makes this a really large positive number. So 1 by an extremely large positive number gives you 0. So you can see that when this is really negative, you converge towards 0. So if you think about this, your input you can pass through you can do a linear combination with the weight vector W, and if you pass W transpose X through a sigmoid, if your W transpose X is a really big number, then your output is almost close to 1, and you can say that's like a positive class. And then if you get a really negative number, then you can say your output is 0 for the negative class. So if you can learn the weights W such that for your positive class, W transpose X is a very large number, and for your negative class, W transpose X is a really negative number, then you can actually separate these two classes, even with a sigmoid neuron. Okay? And the benefit of sigmoid is, compared to the hard threshold for perceptron, this is a smooth continuous function, which means I can actually differentiate this function and easily compute a loss gradient. So that's why it's better if your nonlinearity is a continuous function, right? Which is not exactly the case for relu. Right? Relu has a sharp bump at this point, so you can differentiate piecewise for the two parts, but it's not a single smooth function, right? But still it works well. But the sigmoid is the classic nonlinearity that is used in most early stage neural networks, right? Now, another thing you can think of is, let's say you have sigma, we define a sigmoid like this. You add a parameter A here, right? Okay, and now I want to compute the slope of this curve at x equal to 0. Okay, so if I compute that, what would I get? This is 1 plus e to the power minus ax to the power minus 1, right? So let's do some basic calculus. What would I get? Minus 1 plus e to the power minus ax to the power minus 2. That's the basic rule of differentiation. And then the chain rule means that I need to differentiate this part again. So what happens when I differentiate the inner term here? This is going to be 0. And then from here, what do I get? E to the power minus ax, but then the minus a would come in the front because it's a constant, right? So then I'm going to multiply this by minus a e to the power minus ax, right? And then I have a minus here, this would go away. So I have a times 1 divided by 1 plus e to the power minus ax, and then e to the power minus ax divided by 1 plus e to the power minus ax. I can partition this into these two parts. Okay? Everyone with me so far?
What is the part of the after the negative 2 supposed to be?
It was a minus a times the exponential is like a fixed point function, right? So this is basic calculus where an exponential function, right? So if I take the differentiation of e to the power minus ax, right? The first part is just the same form, right? E to the power minus ax. But then there is a minus a here that would come out here, right? So if this is rusty, maybe brush up on some, remember your basic differentiation. We're going to need differentiation a lot. Neural network is all about differentiation, so we'll need that. But now look at this part. What is this part? This is exactly my sigma. So this I can write as a times sigma of x, right? And if you think about this, this part is 1 minus sigma of x, right? So you can see that for the sigmoid, if you need to differentiate this nonlinearity, you have a really nice expression where you take this constant a, multiply by the sigma function itself, and then multiply by 1 minus sigmoid of x. Yeah?
What does the constant a represent here?
The reason I brought in an a is because I'm going to take a to the limit. I want to argue that when a is very big, your sigmoid actually converges the hard threshold. So by taking a to infinity, we can model a sigmoid as your perceptron nonlinearity. Okay, that's why I brought in the a here, right? Because if I now compute this sigma transpose of x at x equal to 0, right? What value do I get? This will be a times sigma of x when x is 0.
Towards a half.
It's a half, right? Sigmoid is half at the middle. So this will be 1/2 times 1 minus 1/2, which is a by 4, right? And now what does this is basically, if this is my sigmoid, right? This term represents the slope of the curve at the point x equal to 0. And then if I increase a, what I'm doing is I'm making this slope really, really steep, because a is the slope, a by 4 is the slope. So that means this starts to look something like this, really, really steep. I mean, I'm not able to draw properly, but what I'm getting at is that initially if a is small, it might look something like this, where you kind of do like this. But when a is like almost towards infinity, then you're gonna get something like this. This jump is gonna be really sharp, right? And that almost starts to look like a hard threshold that you have in a perceptron. So a sigmoid in a limit is basically a sigmoid neuron in the limit where you make this slope infinite becomes your hard threshold function. So you can basically approximate a hard threshold perceptron with a sigmoid with a very large value of that slope a. Okay. So that means that I can build a sigmoid that would represent this type of threshold, which is I have a point and then suddenly I have a jump here, and I can represent this. I can, taking the value of a to be very large, I can model a hard threshold with a sigmoid, right? And then this is where I have x equal to 0, right? And then if I do sigma, if I define a function phi of x to be sigma of, like, let's say x minus b, right? That means I can move my threshold to some point b, right? So this is going to be like this. And then I can take another function phi2 of x to be sigma of x minus c, right? Let's say that is like this, some c over here. This is c. These are two hard thresholds which we got from two sigmoids. And then if I do phi1 of x minus phi2 of x, right? If you look at these two functions, up to the point b, they are both 0. Between b and c, only that one is some plus 1. And after c, both of them are plus 1. So if you subtract them, in this portion, the function is 0. From b to c, the function is 1. And after c, the function is 0 because they both are 1 and they cancel each other. So that means if I subtract that, I can actually model this as a small pulse. A small pulse that starts at b and ends at c. Okay? Now once I have a pulse, now I am actually in good shape, because I can choose my b and c to move around this pulse anywhere I want. I can choose the difference between b and c to kind of define the width of the pulse. And now if I have any function like this, right, how would I approximate it? I'm just gonna build up all these pulses. I'm gonna take a pulse like here, another pulse here, another pulse here, and so on. For each of these pulses, I need two sigmoid neurons, which I subtract. and then I can define the width of the pulse as I choose, and the number of pulses. So here in this case, if I have like k pulses here, I will use twice k sigmoid neurons to approximate that function, and I just take each pulse, shift it by an accurate amount, and then I can also choose the height of that pulse, right? And then that way I can actually approximate any function with these sigmoidal neurons. Okay? So that's the idea. I'll make this a bit more concrete next class and kind of make it a bit more formal. So we'll start from here next class. Okay? And for your midterm, today is what is in the syllabus. We'll resume this part after the midterm. Yeah. All right, that's it for today. Thank you.
I was going to say, I guess like when they teach you integration.
Yeah, somewhat, yeah.
Sorry?
It looks like when they teach you about integration and.
Exactly. Yeah. It's like similar.
Is that where it's going?
It's on.
I mean, it's like summing up all these pulses, and then we are in the world of discrete stuff, so we are going to do the summation. But the idea is the same integration. Yeah.
Okay. The only thing that we didn't cover was radial basis function, like all the way thoroughly.
A lot, which is reasonable.
Professor?
Yeah.
Sorry.